morning, my dear students. So, last day we have seen the concept of reversibility. So, in the reversibility, we have seen one example. Then we have seen what are the causes of irreversibility. That one is lack of equilibrium, and another is effect of distributive forces. Okay, and I have explained all these conditions of irreversibility. Now, if you have undergone through the analysis of cycle, so to make the analysis simpler, we take the process reversible. Though we know that in this world there is no process exists which is reversible, but we still consider the process as reversible. That's why the concept comes reversible but in limit. Okay, so what is the concept of the process which is reversible but in limit? So we will take down the same example as the previous one. Just like the raising of this temperature from 20 degrees centigrade to this 80 degrees centigrade. Now in the previous cases, in the previous day we have seen that whatever I have explained, I have explained that the process is irreversible. Okay. Now how do we consider this process as reversible, not fully reversible, but reversible in limit? And what are the conditions for the reversible in limit? So we'll take down the example once again. Okay. So I'm removing all these things. Okay. Now we are raising the temperature of the system from state 1 to state 2, but not in a single process, but we will take an infinite number of processes. How? Suppose we will take an infinite number of thermal energy reservoirs. Just like initially the thermal energy reservoir has a temperature of 20.0 degrees centigrade. Then we have another thermal energy reservoir whose temperature is 20.02 degrees centigrade. Then we have another thermal energy reservoir whose temperature is 20.03 degrees centigrade. That means we can say that the step is 0.01 degrees centigrade. And then finally, after taking an infinite number of thermal energy reservoir and whose temperature are just like this, so 79.80, 97, then 79.98 and 79.99 and finally 80.02. So we have taken an infinite number of thermal energy reservoir, you can see, and whose states are 0.01 degrees centigrade. Now what we will do, we will put this system which is at state 1 over here, and we will put it over a certain period of time. So because of this, a little bit temperature gradient of 0.01 degrees centigrade, the heat will transfer from this body to this body, and after some time, whenever the equilibrium has been reached, the temperature of this system, which was at state 1, will be 0.01 degrees centigrade. Now again, we will move this system to the next thermal energy reservoir, and we will put it over a certain amount of time, so that the equilibrium should be attained. And after the equilibrium has been attained, the temperature will go on to 0.02 degrees centigrade. And finally, then moving it from the next thermal energy reservoir to next thermal energy reservoir, and finally we reach to this 80 degrees centigrade. And it will take an infinite number of time. Okay. And for each and every step, and for each and every thermal reservoir, we are putting it over there. It will take a certain amount of time, and for each step the equilibrium will be maintained. So as the equilibrium will be maintained, so we can say that this condition is not fully satisfied, but almost has been satisfied. That means it is so small that we can consider this okay. This one is reversible process. Though the process is not reversible, but still we are considering, we are neglecting the minor effects. Okay, so we can say that this process is reversible, but in limit, where the thermal equilibrium, for this case, the thermal equilibrium is maintained. Now, for if any certain processes, if these equilibriums are maintained, then we can say the processes are considered to be the as in equilibrium or as a reversible process, but in limit. So in this case, we are seeing that the temperature gradient del T is not equal to 0, but almost equals to 0. We are neglecting the minor effect or the minor temperature gradient. That's why we are considering that this process, this heat transfer, as a heat transfer which is reversible but in limit. This is the way to convert the processes into irreversible process to reversible process but in limit, so that it will ease our calculations or ease our analysis whenever we will do the analytical part of any cycles. Okay. Now, what will be the consideration? So I have given you one example of thermal equilibrium or thermal heat transfer. So, and the condition is the del T almost equals to 0. So this is considered as the reversible heat transfer. Okay. Now you can change the limit also. Here the step is taken as 0.01. You can minimize the step, that is 0.001 degree centigrade or 0.00001 degree centigrade. So how much you are putting more steps, or the number of steps increases, as well as the reversibility also increases. So if we increase the step as 0.001 degree centigrade or more than that, that is 0.001 degree centigrade, so it will be more reversible than the previous one. Okay, so this is the way to convert any process, irreversible process, to reversible process. Okay, and if we increase the step, it will take the infinite number of time or more infinite number of time. So if a process takes infinite number of time, then we can consider as this is a reversible process. So one condition for a reversible process is that the process must be infinitely small, will go through infinite small step, and it will take infinite amount of time. That I was explained about the quasi-static process. That one condition of reversibility is the process should be quasi-static process. Okay. So this is the way to convert any reversible process to reversible process. So what will be the condition in the case of reversible in limit? So reversible in limit condition. So to make any process reversible in limit, the condition should be it must maintain del T almost equals to 0, del P almost equals to 0, and del mu C almost equals to 0. So this is the condition for reversible in limit. And what is the condition for if we tally it with the reversible process? If we tally it with reversible process, then del T equals to 0, del P equals to 0, del mu C equals to 0. So this is the basic difference between reversible process and reversible, but in reversible in limits. So these are the conditions. So for reversible process, del T is equal to 0. For reversible in limit, del T almost equals to 0. Del for reversible process, del P is equal to 0. Reversible limit, del P almost equals to 0. Reversible process, del mu C is equal to 0. Reversible limit, del mu C almost equals to 0. So these are the conditions. So if we want to convert any reversible process to reversible process but in limit, the process must maintain these conditions. Okay. So this is all about the concept of reversibility. Now, if we plot a curve, if we plot a curve just like this. Okay. So there is a temperature gradient. And this is the degree of irreversibility. Time. So, if you want to transfer heat, like this. So this is the temperature gradient. So if we go above the temperature gradient, decreases. The temperature gradient decreases. So as the temperature gradient decreases, we can say the degree of irreversibility also decreases. The degree of irreversibility also decreases. So as the temperature gradient is narrowing down, we can say the degree of irreversibility decreases and degree of reversibility increases. Okay, so this is the curve for degree of irreversibility. Thank you.